Okay, section 9.7, it's called the law of sines and the law of cosines. It's got one additional rather important thing in it too. But if I had to give a title to this section, I'd probably call it, as a general rule, as a general thing, oblique triangles. Oblique means not right. In our case, it means not a right triangle. It doesn't mean wrong, it means it's not a right triangle we're talking about. Oblique triangles can be acute or obtuse. Remember what acute is? Acute is where all three angles are acute. Obtuse is where one of the angles is obtuse. Yeah? So we're expanding our discussion to, because we've been talking about right triangles now for the last 3 or 4 sections, and the first section too. Now at the very end of the chapter, we're going to expand the ideas that we learned into things that are not right triangles. It requires 2 laws. And we will get to those laws in just a minute after I take care of the other, or the third topic that's in here. So on page 508, before we really get started with the nitty-gritty, I want you to take a look at example 1. Should be pretty easy to do. Look at example 1, page 508. It says, use a calculator to find each trig ratio, round your answer to 4 decimal places. It just wants you to practice doing trig operations on angles bigger than 90. You haven't done that yet. It's still going to turn out with values, but sometimes those values turn out negative. So just want you to try it so that you can kind of see what to expect. So everybody find the tangent of 150. You should be getting negative 0.5774. So what you're getting?
Yeah.
So don't let it spook you if you start getting answers that are negative, because when we take sine, cosine, and tangent of angles bigger than 90, sometimes they're positive and sometimes they're negative, and it shouldn't bother you. So everybody find the sine of 120. That one happens to be positive. The sine of 120 is 0.8660.
Say it again.
0.8660.
Yep.
And the cosine of 95, which is also an obtuse angle, that one is negative. Negative 0.0872. Okay. What? 0.0872. Yeah. Okay. So they just wanted you to try that out so that you understand that you can get negative answers for some trig functions if you're doing things that are bigger than 90 degrees. All right, so that's cool. Now I'm going to talk to you about the area of a triangle. This is the kind of the odd concept today. It doesn't belong with the others, because the others are about finding sides and angles. This is about finding the area of an oblique triangle, which can be very, very useful. You take a look at the, I don't know if I want to introduce all of those things. This is the main thing for area. This is the nuts and bolts of it. You know, I could explain it to you. It would take a while, but I could. If you have an oblique triangle, say an obtuse one like this, and you know one of the sides, and you know one of the other sides, and you know the angle in between them. So what I'm saying is the given information is in the pattern that you learned to recognize when you were doing triangle congruence. The pattern of the given information is side, angle, side. If you are given a side and an angle and a side in that order, side, angle, side, with the angles in between the two, then this is your formula. I'm going to do this example. It's going to be, so you can, and I'll write it down in general in just a minute. But the area of the triangle, that's the space inside in square units. The area will be 1/2 3 times 10 sine of 110. In a general way, I mean, that's how you would apply it to this one. I probably should have done the general first, but anyway, if I have a triangle very similar to that, and I know that this is A, and this is B, and this is theta, theta is a Greek letter T that's used for representing angles, then the area of this one would be 1/2 AB sine theta. So in a general thought process in your brains to do these, to find the area if you're given side, angle, side pattern, to find the area of that triangle, you take 1/2 of the product of the sides, so you multiply the together, and you assign the angle. And all 4 of those things get multiplied. It's 1/2 times A times B times the sine of theta.
Is it always sine?
It's always sine. Yep. So to do this one, I would do, if I was going to do it in my head, I can't do the sine of 110 in my head, but I can take this 3 times 10 is 30 and half of that's 15. You can do the arithmetic in your head if you want, or you can just plunk it in your calculator. If you want to just plunk it in your calculator, you might put 0.5 for the half, and then a time sign, and then a 3, and then a time sign, and then a 10, and then a time sign, and then a sine of 110. You could do that. I prefer to do the arithmetic in my head, and then all I have to type in is 15 sine 110. And that will be it's really weird, and I could develop it for you a little bit better. I can show you where that formula comes from, and maybe I'll do that if some of you are interested later. But it's a proven thing. People have been using it for thousands of years. So then this one right here would just be 15 times the sine of 110. I'm going to be in the right mode. I am. Okay. That's why I get an area of slightly more than 14. Is that what you're getting?
Yes.
Okay. So I've given you an area formula that's different from, and I need you to understand it's different from this one. This is, by the way, this one stems from this. Usually when you find the area of a triangle, we take the formula that you learned in like 3rd grade is 1/2 base times height. But in order to use that, you have to have a base number, which we don't have here. It might like a 4 or something. Well, no, it would have to be more than that. It has to be like 14. And you also have to have a height, which is a segment, it's an altitude inside the triangle that you have to draw and find. And in order to use this one, you'd have to take 14 times, if I told you this was 5, you'd say 14 times 5 and then cut that in half. But if you don't have those things, and instead you have these, this is another way to find area. This is the familiar one. This is the new one. Does exactly the same thing. Depends on the given information. If you're given a base and a height, then you want to use this one. If you're given an angle side angle pattern, you want to use this one. It's just a new formula for finding the area of a triangle. You okay with that?
Yeah.
Yeah.
All right, moving on. Now we're going to get to the nuts and bolts of the actual the title of this section, which is a lot of sines and cosines. We're going to do sines first. And it's a law, and yes, sine and cosine come into it, but not like they did when they were in right triangles. It's an extension of how we can use them. So consider this with me for a minute. I've got a triangle. It's an oblique triangle. I'll make it acute. That looks like a right angle, but it isn't. We'll say that's an acute triangle, and I have just put some letters on here so we can see them. This will be A and B and C. So this is not a right triangle, so I can't use regular old right triangle trig where we have opposite over hypotenuse and adjacent over hypotenuse. That's not coming into this now. Sorry, it's an extension of what we're going to use. And since this is oblique, and I wanted, if I want to see how these things are, oblique means not right, how these things are related to one another, I'm going to have to fall back on something that I am familiar with. So I'm going to drop an altitude right here. And I'm going to call that H for height. That's different from all the other letters I've done. And if I drop that altitude, I have 2 right triangles, which we know something about, right? Mm-hmm. So can anybody tell me, using right triangle trig, what the sine of C is? H over A. Good. Opposite over hypotenuse. Can you tell me what the sine of A is? A over C. Is that right?
Yeah.
Because with respect to A, this is opposite and this is the hypotenuse using this little right triangle. Do you agree?
H, not A.
What?
H, not A.
Oh, H. Thank you. That's what I get for talking while I'm writing. Thank you for that. That's good. It is H over C. So now I'm going to, now that I've got these 2 facts based on that altitude that I dropped there, I'm going to do some algebra on these things. Remember what we usually do when we have something like this is we cross multiply. That would give me A sine C equals H. If I do that over here, I get C sine A equals H. And that looks like a capital C, and it isn't. It's a little c. You understand the cross multiplying? Both of those things, this thing right here and this thing right here, are both equal to H, and H is the same thing in this picture, which means that I could write A sine C equals C sine A, right? Because they're both equal to H, they're equal to each other. And now I'm going to do something that probably wouldn't occur to you to do, but it's perfectly legal to do. What I'm going to do is I'm going to divide both sides by little a, and at the same time divide both sides by little c. And it looks like this. The sine of c over little c, that's dividing by the c over here, equals the sine of a over little a. That's a legal thing to do. I divide by both of those at the same time and they end up in the denominators there. The reason I did that is for you to be able to memorize and learn this a little easier. And it's in the book this way. What this says is that the sine of angle C over its opposite side is equal to the sine of angle A over its opposite side. And I could, if I were to draw another H here, like this, if I were to draw an H up like this, I could also do the same thing with angle B. You're just gonna have to trust me on that because I haven't got time to show you everything. But we could do the same thing with these two right triangles and have an angle A and an angle B and have the very same thing. And what it will turn out to be is this, that the sine of C over little c is equal to the sine of A over little a is equal to the sine of B over little b. They're all equal to each other. This is the law of sines. But I don't want you to memorize it by the letters. What I want you to memorize is that in any oblique triangle, non-right triangle, without the altitude, because we're not going to draw altitudes, that was just to develop this. Just take this oblique triangle. What I want you to memorize about the law of sines is that the sine of an angle over its opposite is equal to the sine of any other angle over its opposite. And you think, well, what about the third one? I need you to understand this as well. All of these are equal, but you will only use them two at a time. You might use C and A so that you have a proportion with one equal sign. You might use those two together. You might use these two. You might even use these two, but you will never use all three at once. And the main idea is the sine of an angle over its opposite equals the sine of an angle over its opposite. And that forms a proportion that you can cross multiply and solve. Two at a time. Okay? So let's take an example. I'm going to erase the whole thing and apply it. Remember, it's not letters that we memorize. It's the idea. The sine of an angle over its opposite equals the sine of an angle over its opposite. That's what I'm going to use on this next one. So I'm going to erase this. I'm going to put a triangle up here. It's going to be an obtuse one. I'm looking at example 3 if you want to look at it too. There's an obtuse triangle. Comes across like this, 115. This is 11. This is 20 up here. A, B, and C. Notice that C is no longer opposite the longest side. Now all those bets are off. That's just, and here's little c, and that'll do it. And the instructions are, solve the triangle. You know what that means. Find all the missing pieces. They gave us 3. They always will give you 3. And you have to find the other 3. So the things we have to find are little c, angle big C, and angle B. Those are the ones missing. Everybody okay? Yeah.
Angle A, if it's in the diagram, it's 135.
Is it?
No?
Somebody point out which example one. We're on example 3 on page 509.
Example 3, okay, I was looking at it.
Okay, that's okay. That's all right. Okay. So here we go. We're going to try to see if we can find those 3 things. And I'm going to say, I'm going to use my law of sines, which would be like this. We'll say the sine of 115 over 20, see it?
Yes.
Sine of an angle over its opposite equals the sine of an angle. Which angle should I use? If I use angle C, it will be the sine of C over little c, and I'll have 2 variables. So I'm forced to use this one because I don't know what angle B is, but I do know that its opposite is 11, and that will leave me with 1 variable. So you have to choose carefully. I'm going to say the sine of B over 11. Do you see why I'm doing that one? Instead of the C's, I hope. You can't just choose whatever you want. You got to choose what you know the most about. We know the most about B and its opposite. We don't know anything about C and its opposite. So that gives us a proportion. The sine of an angle over its opposite side equals the sine of an angle over its opposite side. We cross multiply like this. Okay, that flattens it out. It takes the fractions out of it. And then it's a little more clear. We're trying to find B. We've got to do two things. We got to get rid of the 20 and we got to get rid of the sign. We got to do it in that order. This is 20 times the sign of B, so I'm going to divide both sides by 20. And I'm not going to grab my calculator yet. That's pretty easy algebra move, right? Right? Then we got to get rid of the sign by doing its inverse, which is inverse sine. If I inverse sine this side, I will get B. But I have to inverse sine this side also. And in your calculator, you have many, many options on how to calculate this. But once B stands alone, then you can grab your calculator. A lot of people do this first, and then they say inverse sine of the answer. Does that make sense? Okay, so this is how I would do it to avoid using a whole bunch of parentheses. Me personally, I would find the numerator of this and hit enter. So I would say 11 sine 115 and hit enter. Then I would divide it by 20 and hit enter. And then inverse sine that. So I would go second sine of second negative sign, which is answer on my calculator anyway. And I get 29.9 rounded to the nearest tenth. Are you getting that?
Mm-hmm.
So that goes over here in my little list.
You got what?
29.9 degrees. Did you?
Yeah.
Okay. Now the cool thing about this is if this is 29.9, we can easily find this one by subtracting these two from 180 without having to go through this process again. Right? Okay, so I'm going to take 180 minus 115 minus answer because that was my 29.89 business. And I get 35.1 for angle C. Not only am I going to write it here, I'm going to write it here as well. Because I'm going to need that to find little c. Can't use Pythagorean theorem here because this is not a right triangle. So to find little c, this is what I'm going to write. I'm going to say the sine of answer. Because the most recent answer that I have in my calculator is this one. And I want to sign that, but I don't want to sign 35.1. I want to sign 35 point all this crap that follows behind it so that it's as accurate as possible. So I want to sign answer over little c equals, and I don't want to use this because this was an approximation, so I will use the sign of 115 over 20 again because they're exact. Okay, then I'm going to cross multiply 20 sine answer equals sine or c sine 115. Notice I haven't punched anything in the calculator yet. I'm trying to get at little c, so I'm going to have to take this side and divide it by the sine of 115. Now, the most recent answer in my calculator is still that 35.1 blah, 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 that I don't want to approximate. So now I'm ready to calculate this. What I'm going to do is I'm going to take 20, and I'm going to type sine, and then go grab that answer and hit enter. So I have a numerator. Then I'm going to divide by the sine of 115. And I get 12.7. Did you catch that? Are you sure? Okay. If anybody wants a picture of this, you might want to take it. You might want to do that now. If not, the answer, the way that to do it is in the book. The author's done a good job writing it up too. So you're welcome to go back to that. That was a lot of new stuff. We were only given two sides at an angle, and you went after it using what as much about what you knew as possible. When we got that, we recovered this angle. Then we had to use that angle and the law of sines to recover this side. It's hard. And it's lengthy, and there's a lot to it. Because we are recording this right now, I'm not going to give you a chance to do one on your own. We'll do that. We'll do that before I give you the assignment in a few minutes. But I want to just let this thing run while you guys are doing the problem. Okay. All right. So take a look at example 4. And example 4 says solve the triangle. Round decimal answers to the nearest tenth. I'm going to go faster through this one since you've seen one pretty slow here. I'm going to get rid of it. put one up here and I'm gonna go faster through it. You can either watch or you can try to keep up. That's up to you, but I'm gonna be grabbing my calculator when I'm talking to you about what I'm doing all the way through it. And please do what you've been doing, which is when I look at you and say you get it, nod at me or give me a frown or something so I know whether I'm getting through to you or not. So here's another sample of an oblique triangle that's obtuse. This is 107. This is 15. This is little a, so this is big A. This is little c, so big C's up here. Here's B. And the instructions are solve the triangle. So we go. Well, first of all, I want to figure out what I need. I need angle A. I need angle B.
Angle B
And little c.
is 25 degrees. It has it on the.
What? Oh, did they give us that too?
Yeah.
This is 25?
Yeah.
Oh, I guess they would have had to. So it's angle B, we know, and it's angle A I need, and little a and little c, right?
Yep.
Okay, well, angle A is the easiest one to recover. If they give you two angles, you can get that third one quick. Okay, so let's do that first. So in my calculator, I just type 180 minus 107 minus 25. $48. Put that here, and I'm also going to put it in my picture so I know where it sits. Now I'm going to go after little a first, and that's going to be the sine of 48 over little a equals, and it doesn't matter where the variable is, the sine of, and now look at what I've got here. I can't do the sine of 107 over little c because that will give me two variables. So I look at that, I go, nope. And I look at this, say sine of 25 over 15, because I've got all of those pieces. Cross multiply. Divide. Calculate. And I get 26.4 for little a. That seem right? You get the
Yeah.
same thing? Anybody that's trying this? Now we're going to do the same thing for C. It's going to be the sine of 107 over little c equals this same one here because it's not approximated or anything like that. Sine of 25 over 15. 15 sine in the cross multiplying of 107 equals c sine 25. And so we divide this by the sine of 25. We have c. And I get 33.9. Is that what you're getting? Those of you trying it? Anybody trying this?
You go too fast.
Well,
Yes.
get those fingers moving.
Yeah.
That's what we're getting?
Yeah,
Okay, so that's another triangle solved in a slightly different way. We were looking for two sides this time. And since we had two angles given, finding the third one was easy and we just ran with it. Look at example 5. This is a use of law of sines to actually do something practical. It says a surveyor makes a measurement shown to determine the length of a bridge to be built across a small lake from the north picnic area to the south picnic area. Find the length of the bridge. From the north to the south, looks like we're looking for angle C. I'm sorry, little c. Right?
Yeah.
And if he has measured those things off with a, I think it's called a, instrument we use. Transit. He's measured these things off from A, B, and C in these angles right here, and he measured the angles with the transit and also the distances using sonar, I bet you. And so in order to find little c, can you understand that we would write, well, first of all, he doesn't know how big angle B is, but it's pretty easy to come up with, right?
Mhm.
So I would find angle B first, and then I would say the sine of that angle over 150 equals the sine of 60 over little c. Now I have my answer. I'm not gonna do that for you, I just want to see it. You see that. We had to find an angle which was pretty easy so that we could use it with the opposite side, 150. But, I'm just gonna find it real quick so I can talk about it. So we do 180 minus 71 minus 60, and we get 49. So angle B is 49. So to find little c, you would say sine of 49 over 150 equals the sine of 60 over little c. Cross multiply and solve. Does that make sense?
Yeah.
Okay. I'm gonna move on then to something else. Take a look at this new triangle. That has this given information. Hang in there, guys. I know, just hang in there with me. This is a long lecture. Okay, so this is our given information on this one. And if we're going to use the law of sines on that, we would say, for example, the sine of 34 over b, sine of that over its opposite, equals what? If I write the sine of a over 11, I've got two variables, side b and angle a. If I do the sine of c over 14, I've got two variables, angle and little b. In this particular instance, there is no way to use the law of sines to solve this. And so we need something else. So I'm going to erase this right here and come back to it in just a minute. We're going to do this again. And this time, I don't expect you to actually follow or actually come up with this proof of the law of cosines, which is what we're going to do, but I expect you to follow what I'm doing. See if you can understand what's happening. So that's not a right angle. It's ABC. A, C, B. And we're going to drop an altitude again, but we're going to try to come up with something new. Actually, in order to be able to follow the paper that I have here somewhere, where is it? I have it. I'm going to reletter these things so it follows what I'm doing and I don't have to make it fit. So hang on a minute. I'm going to call this B, A, and C, little a, little b. I'm going to put little c down here because there's something I want to do here. I'm going to call this part, this piece right here, I'm going to call that x. And you think about it, that makes this one c minus x. For example, if c were 17 and this was 11, this would have to be 6 because 17 minus 11 is 6. Whatever this full length is here is c, because it's opposite big C. That whole length there is c. If I put x down for a piece of it, then c minus that x is what's left for this piece. Does that make sense algebraically in your head? Okay. Now, can anybody tell me why this should be true right here? By the way, I dropped that altitude and this is h. Again, we'll call it h. Why a squared equals x squared plus h squared. Why should that be true? Yeah, Pythagorean theorem is the reason. Because in this triangle over here, c minus x is one of the sides squared plus the other leg squared, a squared is equal to a squared. I put the a squared in front. That's Pythagorean theorem. It's telling you each of these things I'm about to write here are reasonable. That's the Pythagorean theorem. Now, tell me how you believe this thing that I just wrote here could evolve into this. What is it? How does this become this? Here's what you look at. Try to figure out what has changed. A squared is still a squared. There's an equal sign. Ooh, this is not the same at all. We got a plus h squared on the end, but this somehow transformed into this. What do we do? The word that we use commonly is we FOILed it. We took c minus x times c minus x. You understand that that's what you get when you do that? Who's wondering? I took, because of c minus x was a binomial and I squared it, this is the result of squaring a binomial. That is FOILing. Okay. Now, how does this become this in the next step? This one may be a little bit harder. It's a squared equals c squared minus 2cx plus h, no, b. And again, you look at what's changed. A squared still there, equals c squared minus 2cx. Oh, somehow this piece here got transformed into b squared. Look at your picture and see how you can convince yourself of that.
Because the other half of the triangle is x squared plus h squared equals b squared.
Right, so x squared plus h squared can be replaced with b squared by the Pythagorean theorem and substitution. Did you understand what she said based on the picture? Look over here. X squared plus h squared is equal to b squared because of this right triangle. Pythagorean theorem. X squared plus h squared equals b squared. So wherever I have an x squared plus h squared, I can replace it with b squared. That's Pythagorean theorem and substitution, putting that into place of it. Is everybody clear on how we got to there?
Yeah.
All right, hang in there with me because this one's rough. Let's see if you can find this one. I'll give you a minute to think about it. A squared equals c squared minus 2c times b cosine A plus b squared. That's a tough one. So let's point out what's different and see if you can come up with the reason why it should be that way. There's a squared still the same, equals c squared minus 2c, and then a plus b squared. This x right here, just that x right there, is somehow equal to b cosine A. Look at your picture and see if you can see why that should be. And let me give you a hint. Start out with the cosine of A. Think in your mind, what's the cosine of A? Tell me that. Cosine of A is x over b, isn't it?
Yeah.
So cross multiply, what do you get? B cosine A equals x. So wherever there's an x here, I can replace it with b cosine A. See it? So this is, the reason why this one was tough is three things. It was the definition of cosine, then cross multiply, then substitute. That's hard to see. Definition of cosine was this, cross multiply gave us this, and then we replaced x with b cosine A. Everybody good? Yeah? Now how about this is the last step. A squared equals c squared plus b squared minus 2bc cosine A. How do we get from here to here? Here's a squared equals c squared. Oh, where'd that come from? Oh, it came from the back end. I decided to put it right there. See that? I just tucked that plus b squared right in there, and then there's your minus 2. Oh, this was cb and this is bc, but that's okay because you can multiply in any order, right? Okay, cosine A. It's all there. It's just been rearranged in such a way that it looks like what's written in the book. This is the commutative, means you can move it, property of addition here, where we move the b up here, and multiplication here, where we switch c and b around. Actually, you know what? I'm going to make this b squared and this c squared. I'm going to do a little bit more switching. That's okay. It's still this for this reason. And again, I don't want you memorizing. This is the law of cosines, by the way, in case you were wondering where we were headed. This is the law of cosines because it has a cosine in it. And I don't want you memorizing it by the letters. It will not serve you well when you have a triangle that's got an RS and a T in it instead. It will not if you memorize it just for the letters. Here's what I want you to notice. That in this triangle, notice there's no H left, so I'm going to erase this so it doesn't cause us any confusion. In a triangle, if you take a side squared, then the cosine of its opposite angle is on the other end. When you start out with a side, whatever that side is, the cosine of its angle is over here. So that begins and ends with A's in this case. A here and cosine of A here. Everything in between is the other two sides. We've got a b squared. That's the one of the other two sides. We've got a c squared here. And we've got b and c showing up again, single here. This -2 you have to memorize. But it's like bookends. This right here is a bookend with this. We have a side and the cosine of that side here. Everything else in between is made up of the other two sides. We square them and add them here, and we take -2 times them here. That's what you have to memorize rather than the letters. So with that in mind, with that in front of your eyes, and we have a specific situation here that sines did not work on, I'm going to erase this because it's going to be in my way in a minute. I wanted to find little b first. I have to find b and capital C and capital A. I got to find all of those. But if I wanted to find little b first, I would say b squared is equal to 14 squared plus 11 squared minus 2 times 11 times 14. Those two guys that you squared there go here. Cosine of 34, the opposite of b. You see that? You see that's an application of this? Here's a side. Here's the cosine of its opposite angle. All this stuff in the middle is made up of the other two sides. 14 squared here, 11 squared here, 11 and 14 here in either order, doesn't matter. And then the cosine of 34 on the end. That's something you're going to have to get used to and memorize and get it memory. You don't get a cheat sheet for this test. Then when it comes time to calculate that, you can actually type it in exactly as you see it. 14 squared, just type it in, plus 11, make it squared, minus 2, parenthesis, 11, close it, open another one, 14, close it, cosine, 34. You hit enter, you find that little b is 61. What did we forget to do? No. Square root it. This is b squared. 61 is b squared. It should cause you to think about it a little bit harder. You see this 11 and this 14, you say, 61, that can't be. And you're right, it can't be. That's b squared, what you just calculated on this side. Don't forget that when you get this as a number, you have to go square root, answer. B is 7.85. 7.9 if you want. To the nearest tenth. That seems a little more reasonable. With these other sizes of angle or sides here, 7.9 seems a lot better. Okay, now, the author of the book says, now that you know what this is, you can use the law of sines to find this and this. You can go over to the law of sines. And I say, don't do that. Don't ever do that, because in about 15% of the cases, it has to do with the size of the angles. In about 15% of the cases, going to the law of sines at this point will not give you the correct answers. All the ones designed in this book for your exercises will work if you jump to the law of sines right here, and it's fine. You go right ahead. When you get to the actual class called trig and you pull that, you're going to be wrong some of the time. To be right all of the time, the rule is if you start out with the law of cosines to find something, stay with the law of cosines until you're done. That will get you the correct answers 100% of the time. Well, if you do them right. So don't jump to the law of sines here. The book recommends you do, and I don't. I don't like that because he's contrived, the author of the book has contrived the problems to all work out if you do jump to the law of sines at this point. And I don't like that. I want something that'll work every time. So I've still got to find angle A and angle C. Here's what I'm going to do. I'm going to go after angle A. That means I have to start out with the opposite side because the cosine of A is going to be on the end here. You see what I mean?
Yeah.
Take the opposite side and square it equals. And then I'm going to take, I start out with the 11 squared. So now I'm going to go to 14 squared. Plus, and if you really want to be accurate, you'll say answer squared. The answer is this 7 point, all this stuff that we, 7.8521607, right? That's what we want to square root our square here. Minus 2 times 14 times the answer. Cosine of A. Look at how many prison doors A is locked behind. It's locked behind a cosine. It's locked behind these three things multiplied here. It's locked behind this one. It's locked behind this one. How are you ever going to get at that? And the answer is carefully and algebraically like this. First of all, it's something I need to point out that's very, very critical. This is a term, a little tiny term there. This is a term. This is a term. A lot of people, when they go to calculate this, want to go 14 squared plus sine or plus the answer squared minus 2 times 14 times answer, and then divide that by over here. You don't do that. This is a term. This is a term which needs to be gotten rid of first. Then you divide by this piece right here in front of the cosine of A. Because order of operations says you have to do multiplying before you do adding and subtracting. If you do this subtraction here with this multiplication sitting there, you're going to be wrong. So this is how you do it. You take the 11 squared, you subtract the 14 squared, and you subtract the answer squared. That gets rid of these two terms by subtraction, coming over. Then what you're left with is, and I'm going to erase this so I can save a line. I brought those over to the other side. Now what you're left with is this. And we need to get at this by dividing by negative 2 times 14 times the answer, like this on both sides. And we will get the cosine of A over here. When you find the answer to all this junk, you inverse cosine it. So, here's what we do. We take 11 squared. I'm going to get my numerator first again. So I'm going to go 11 squared minus 14 squared minus that answer. That was 7.8521607. Go grab that and square that with your answer. Then hit enter. Now, when you go to divide by this, you have to put it in parentheses, because if you don't, your calculator will only divide by negative 2 and then take that result times 14 in the answer. You don't want to do that either. So we've got to put that in parentheses. So we're going to say divided by parentheses, how you start. Negative 2 times 14 times that answer. And you'll probably have to type that one in, because I'm sure your answer has changed since then. So it'll be 7.8521607. You're going to put all of that in there and close the parenthesis and hit enter. And you get 0.62155 blah, blah, blah. 0.62155, a whole bunch of stuff, equals the cosine of A. So to truly find A now, you say inverse cosine. So you hit second and the cosine function and then the answer. And we have not approximated anything. The answer is 51.6 for angle A. When you round it to the nearest tenth. Is everybody clear on that? Now, happily, if we find this one, which we just did using the law of cosines, and it was rough, we can find C now by simple subtraction. So 180 minus 34 minus answer. It's going to get us 180 minus 34, I messed it up, minus that, 94.4. Finding one of the missing angles using the law of cosines can be really, really labor intensive as far as the algebra goes. You make one little mistake and you'll screw it up. If you do not get a number between 0 and 1, you've done something wrong, because you can't inverse cosine anything that's greater than 1. Law of cosines can be tough, especially when you're going to use it to find an angle. I know you're sick of listening to me. I'm kind of sick of talking, but you got to listen for 2 more examples, so hang in there. We have all the laws out here now. And if you've written them down, then you should be able to look at them as I'm using them and see how it's going, how it's working. You can also look at this video if you want to see this one worked out again for all the details on that law of cosines. When you're looking for an angle with the law of cosines, it can be tough. Until you've done 3 or 4 of them, then it's not so bad. Okay, so I want you to look at example 7. Yep. Example 7, this one's got no angles given to you at all, but it has the 3 sides. Let's get an ABC this way. And this is 12, 27, and 20. And that's all you get. You only get the sides, no angles. Which means that we've got to go find at least 2 of the angles the way I just showed you. So you're gonna see another 2 examples of how to find an angle using law of cosines. So, just so you know, law of sines is not appropriate here because the sine of A over 12 and the sine of C over 20 or B over 27 is going to have too many variables in it. So you have to use law of cosines. Which angle would you like to find first? And it doesn't matter. Just tell me which one. A. We go after A first. That means we lead off with 12. You understand? So we start out 12 squared equals. Now we go to the other 2 sides. 27 squared plus 20 squared minus 2 times these 2 guys that are not squared. Cosine, it's always cosine because it's a law of cosines, A. And we've got to unlock that A by doing what we just did in the previous example, which is to start out this way. 12 squared minus 27 squared minus 20 squared divided by negative 2 times 27 times 20 equals the cosine of A. Is that too much algebra for you to follow? I took the 12 and I subtracted this over to the other side and this over to the other side. And it gave me this numerator, which left me with this. So I divided by this stuff, which is on the front of the cosine right there. Do you see it? If you can do that, then this won't be that bad. But calculating can be rough. You got to be really careful how you calculate this. If you want to calculate this all at once, you can. Just make sure you wrap your numerator and your denominator in parentheses of their own. You can do it all at once if you want. That's what I'm going to do. So I'm going to start out parentheses. 12 squared minus 27 squared minus 20 squared. Close that numerator parenthesis right there. Then divided by parenthesis. Open it up. Negative 2. Parenthesis 27, close it, open another one, 20, close it, and close the denominator. Enter. I get 0.91203, stuff. Is that what you're getting? You should try this. Don't just sit up here and watch. Don't just sit there in your seat and watch. Math is not a spectator sport. Do this and see if you can get the 0.91203 that I got, because I can do this. I want to see that you can.
What'd you get?
0.91203, 7037. This is the syntax. Syntax means the way you put it in the calculator. You have to put this in its own set of parentheses before you hit the divide sign. Then you have to put all of that in its own set of parentheses. Point 91203, 7037. Is that what you're getting?
Yes. Yes.
Anyone not getting that, I need to come and help you figure out what you're doing wrong. Anyone? I'm happy to come and help you. I'm not even going to beat up on you. I'll even be nice.
9.91.
0.912037037. Anybody need any help? And if you don't want me to come to you, then ask your neighbor what you did wrong and have them look at it with you if you got it wrong. Once you have that, this is a decimal. Now you inverse cosine that answer. So we go second cosine. Okay. Second cosine of answer. And we get 24.2. You all agree?
Yep.
Yeah.
All right. Now, you guys on your own go after angle C. Yes.
What's the second cosine again?
What?
What's the second cosine?
It's the second function of cosine. You go second function and then the cosine key. Because what we have to do is get this cosine off of that A. Whatever this was, which was 0.91, blah, 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 we have to inverse cosine that. That's why I'm saying the second function to grab this key to second function it, to second cosine it. Still not getting it?
So it's inverse cosine?
Yes. But I'm telling people how to enter the calculator by saying second function. Okay. Everybody go after angle C. Try to get it on your own. Anybody have it yet?
Yeah.
Willing to risk telling me what you got?
43.1.
You got that too? We got two 43.1s. We get anything different? So it's kind of a rough deal, but you can do it. This is 43.1. The happy thing is, we don't have to do that for angle B. Just take 180 times these two. And it's okay to go ahead and use their approximated thing, because you're going to approximate this to the same value. So I think it's okay to use those approximations. 24.2 minus 43.1. 112.7? One last thing. I would do example 8, but I think you can handle it on your own. That's got a side situation. Something you may not have noticed that I'm going to summarize for you. If you're going to use the law of sines, then the pattern of the given information has to be either side angle, angle side angle, or angle side. In other words, you've got to have more angles than sides, except for this. This is a weird one. If you're going to use the law of cosines, then you're going to have a surplus of sides. Law of cosines is about sides. So if your given information is in the pattern side, as this one was, or side, as the one prior to it was, if your given information is in this pattern, you use the law of cosines. If it's in one of these three patterns, you use the law of sines. Generally, if there's more angles than sides, you use sines. If there's more sides than angles, you use cosines, except for this situation, when the two sides are minus 2. That's just kind of an odd man out. Okay? And if you start out using the wrong one, you will quickly learn that it's not going to work and you need the other one.
Do I dare ask about when you use tangent?
There is no law of tangent, and thank goodness, because you'll learn in trigonometry that the law of that tangent is equal to sine over cosine. So anything that you can do, anything can be written in terms of sine and cosine. So this is it.
Okay.
These are the only two laws. No law of tangent.
Okay.
I know. There is a law of tangent, but we don't teach it because this handles all possible situations.
Yeah.
These two do. Okay? These two laws.
Right.
Okay, so here's the assignment. Do your best, kid. Don't forget, there's one other thing you learn, which is the area. You know, if it's inside angle side, 1/2 AB sine C. Remember?
Yeah.
Okay, it's right at the very beginning if you get that written down. Anyway, page 513, this is where it begins, and the assignment is 1 to 33 odd, 34, 40, 43, and 44. There you go. Okay,